let's learn about continuity. We're in section 3.2. One of the main applications of limits is to determine when a function is continuous. A function f is continuous at an x value a if, well, I probably should have left that blank, but that's what we have. The limit as x approaches a of f of x equals f of a. Now you might say, well, wait a minute, isn't that always the case? Don't we find limits by plugging in a? Yeah, but that's not always how it works. Remember, we have situations where we might have a function. I'll make this, that's the y-axis just to be crystal clear. And let's see what's going on here. Let me come up with a bunch of examples. Okay, we go here, maybe here, here, and then maybe we do something like this, that, and maybe we can just, that's probably good. We can probably stop right there. Okay, so let's just take a look. If this is A, B, C, D, and we'll call this guy E right here, just right there. Well, let's take a look. Here, for A, let's look at A, right? The limit as x approaches A of f of x equals L, right? By the way, this is y, the graph of y equals f of x, right? Hope we all agree, right? The limit as x approaches a of f of x equals L. But f of a does not exist. So f is not continuous at a. Similarly, limit as x approaches b of f of x does not exist. So f of x is not going to be continuous at b either. Actually, on a similar note, the limit as x approaches c of f of x does not exist, right? Because the left-hand limit does not equal the right-hand limit. Let's do this example, call this guy m. The limit as x approaches d of f of x equals, we'll call that m. Maybe I'll move this down a little bit so I have to come up with another letter. But that does not equal f of d, which equals L, right? Okay. And then finally, here we do have that the limit as x approaches e of f of x does equal f of e, which we'll just say equals n. So f is continuous at x equals e. Maybe I'll point this out in red. F is not continuous at x equals a, b, c, or d. Right, because the limit as x approached a, or b, or c, or d does not equal f of a, or f of b, or f of c, or f of d. Let's take a look at an example. Is the function f defined by this? This is what's called a piecewise function, right, where f is one piece before a certain value of x and another piece after a certain value of x. Is that continuous at a equals 0? Well, let's take a look. What we're really asking is the limit as x approaches 0 of f of x equal to 0? Or sorry, equals, not 0, I lied. It should equal f of 0. Okay, well, to answer this, we need to look at the left and right-hand limits because f behaves differently before and after 0. So, first, let's take a look and see that limit as x approaches 0 from the left of f of x equals the limit as x approaches 0 from the left of e to the x, right? Because that's how f is defined when x is less than 0. And we know that we can just plug in x equals 0, and we get e to the 0, which equals 1. We also know that the limit as x approaches 0 from the right of f of x equals the limit as x approaches 0 from the right of x squared. And that equals 0 squared, and that equals 0. So already we know that the limit doesn't exist, but let's also just point out that this equals f of 0. Okay? So I'll just write here, since the limit as x approaches 0 of f of x does not exist, f is not continuous at x equals 0. Okay? Now, colloquially speaking, a function f is continuous at x equals a if, again, this is just very colloquial, we don't have to lift our pencils at x equals a when we're graphing f of x. Right? We can just draw the graph without lifting our pencil. Now, the same way that we talked about left and right-hand limits, we can talk about left and right-hand continuity. So we can say function f is continuous at x equals a from the left if the left-hand limit, right, the limit as x approaches a from the left of f of x equals f of a. And of course, you might imagine we have a similar concept, except from the right. Right, when the right-hand limit is equal, right? There's left hand, there's right hand. So in example 1, right, we said that f was not continuous at 0, but was it continuous from the left? Was it continuous from the right? Well, it wasn't continuous from the left, right? I'll just write here in green, the limit as x approaches 0 from the left of f of x equals 1, which does not equal f of 0, which equals 0. So no, f is not continuous from the left. However, limit as x approaches 0 from the right of f of x equals 0, which does equal f of 0. Okay, so I'll just write here in blue, or I guess I'll write in green. Well, actually, maybe I'll just copy and paste this stuff right here. Guess I'll just cut it, it's a little easier. Okay, so I'll write here in green, so f is not continuous at a equals 0, I guess I'm calling it x, whatever, from the left. F is continuous at x equals 0 from the right. Okay. One nice thing about continuous functions is that they can be built from other continuous functions. In particular, the sum, difference, scalar product, regular product, or division of continuous functions, and in fact, even composition of continuous functions guarantees another continuous function. So, for example, if I gave you some really weird, complicated function like this guy, is this continuous at 0? Oh my goodness gracious, I have no idea what that function looks like. However, I do know the following. We know all polynomials, if you think about it, this is true, all polynomials are continuous really everywhere. So I'll just say at x equals 0. By fact 2, this means that 8 pi x to the 5th, right, minus 6, right, we just said that that's continuous. We just said that this is continuous, right? They're both polynomials, but this is also continuous at x equals 0. Again by fact 2, and this is since sine is continuous at x equals 0, right? Because trig function, sine and cosine, I should say, are continuous everywhere at any value. I'll just say so is sine of, well, I'm going to copy this guy. So, yes. Okay. So that's all we have to say, right? That's a way that it can be useful to know that, sums and products and compositions of continuous functions are in fact continuous. Okay. Expanding this definition a little bit, we talk about continuity at a point. We can talk about continuity, we can say continuous on an interval. I'll call it C comma D if f is continuous at x equals a for all a in the interval. Now, technically speaking, I have to be a little careful with it. Technically speaking, it's really all a in the open interval. And I should write and continuous at C from the right and continuous at D from the left. If this is confusing, then just ignore it. But maybe pause the video and think for a minute about why that's the case. Okay. Again, we're restricting ourselves to the interval C to D. So anyway, one last example is, for what value C is this piecewise function continuous everywhere? Well, we know that since cx squared, just some constant c plus 2x, and then and x cubed, oops, that's a minus cx, are continuous on negative infinity to 2 and 2 to infinity, respectively. So really all we need to know is whether f is continuous at 2. So I'll say all we need to guarantee is that f is continuous at x equals 2, and then that way we will know f is continuous everywhere. All right, on negative infinity to infinity. Okay. So we need a couple things. We need the limit as x approaches 2 of f of x to equal f of 2. Now, note that not that f is going to be continuous from the right, so really we just need to make sure the limit exists. So I'll say we also need limit as x approaches 2 from the left of f of x to equal the limit as x approaches 2 from the right of f of x. So we need, so I'll say, so solve for c such that limit as x approaches 2 from the left of f of x, which really equals that cx squared plus 2x. we want that to equal the limit as x approaches 2 from the right of x cubed minus cx. Okay? Well, what happens if we plug in 2? We're going to get 4c plus 4, right? Because we just plugged in, let's highlight this for a sec, we just plugged in x equals 2 in for x. Similarly, we're going to plug in x equals 2 in for x right here. And we're going to get 8 minus 2c. So you see, we're just solving for c, right? And a little bit of arithmetic reveals 6c equals 4, and so c equals 2/3. Right? Yeah. So that's it. That's all we've got.